Discrete probability distributions, the second section of unit 23.2. When assigning random variables, they must satisfy the following rule. And it's got 3 bullets there, but all pretty much says the same thing. It says if capital X is a random variable with sample space anywhere from x1 out to xn, because remember we're only doing finite sample spaces in this class. We will not be doing infinite, thank goodness. And those probabilities that correspond to them will be P1 through Pn, so the probability that x equals x1, probability that x equals x2, so on and so forth. It's going to be written like this. Probability that capital X equals xi equals pi, so that just means like, oh, the probability that capital X equals 1 is 1/6 if it's a die, something like that, okay? And all the i's are just telling you how many terms there are, 1, 2, 3, 4, all the way out to n. So if it's a single die, n would be 6, right? So you'd have x1, x2, x3, x4, x5, x6, corresponding P1 through P6. Cool. Well, all probabilities must be between 0 and 1, 0 being impossible, 1 being guaranteed. Makes sense, right? All the probabilities have to be between 0 and 1. Great. So here we have a sigma of pi, and all this says is if you add up all your probabilities, oh, they'd better equal to 1. And if they do, all the probabilities do add up to 1, then the set of probabilities decides a probability distribution for x. There you go. If they don't add up to 1, well, then they don't make a probability distribution for x. That's all there is to it. So for example, you're going to toss a coin 2 different times. Ding, ding, toss it twice. The number of heads that you could get, well, you could get 0, you could get 1, you could get 2. That's what it's telling you. The probabilities those happen, well, if you get none, that's tails, tails. That's 1/2 times 1/2, 1/4. You could get 1, so that's tails, heads, or heads, tails. That's 2 out of 4, and then which reduces to 1/2. And then obviously you get 2 heads, that'd be heads, heads, which is 1/2 times 1/2, or 1/4. You see all of those probabilities, 1/4 and 1/2 and 1/4, they are between 0 and 1, and if you add them up, 1/4 plus 1/2 plus 1/4, they add up to 1. So that is the probability distribution of x. Now, probability distributions can be given in table form, which is actually how you see it often. You often see them done in tables, especially in the IB exam. Graph form, which we're going to be making graphs and tables, or a probability distribution function, also known as a probability mass function. The domain of the probability mass function is the set of possible values of the variable. So those would be the x1s through xn's, and the range is the set of probabilities, P1 through Pn. Okay. Let's just jump right into it. We have 3 examples. So a magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1 magazine. 38% purchased 2, 21% purchased 3, 13% purchased 4, 5 purchased 5. Part A just wants to know what is the random variable. So you would just say, well, the random variable x, say capital X, is the number of magazines sold. So the values that capital X could take on, 1, 2, 3, 4, 5. Notice that we weren't told 0 magazines. I guess we're assuming that if you walk into the store, you're buying a magazine. So the values that X could take on, which would be the domain, are 1, 2, 3, 4, 5. The range, the Y values, are actually the probabilities that they gave you, those percentages. But rather than putting them as percentages, we're going to put them as decimals. Part B says make a probability table for the random variable. So let's do X and P of capital X equaling X. And you know what, if it helps you, tell you what, let's make those fancy X's, that way it's more obvious. The little x will be fancy. Like that. So we have 1, 2, 3, 4, 5. Right, 1, 2, 1, 2, 3, 4. There we go. That'll work. Now I could box it in, but meh, who cares? little x could be 1 magazine, 2 magazines, 3 magazines, 4 magazines, or 5 magazines. The probability of 1 magazine is 0.23, 0.23. Probability of 2, 0.38. I don't have room for my zeros. 3 is 0.21, 4 is 0.13, and 5 is 0.5. 0.05, excuse me, 0.05. Cool. We make sure those add up to 1. Let's see, 50, 61, 82, 92, 95, 100. Yes, okay, it does add up to 1. Cool. Part C says to graph this using a spike graph, or you could use a bar graph if you like. It actually doesn't matter, spike graph, bar graph. They said spike graph, so let's do spike graph. Which is cool because we haven't done any spike graphs yet. And let's see, 1, 2, 3, 4, 5. Numbers of magazines, and what did I do on the left? I just went by 0.1s. So 1, 2, 3, 4. This is 0.1, 0.2, 0.3, 0.4. 1 corresponds to 0.23, so just a hair above 0.2. Put a little ball on the end of a stick, like a little lollipop. Spike graph. 2 is almost 40%, almost 0.4, so a little ball, lollipop right below 0.4 to the best of your abilities. Make my lollipops bigger. I know it's ugly, it's terrible. 3 should be also just a hair above 2, but just a little bit shorter than 1. Doing my best. 4 is 0.13, so a little bit above 0.1. And the last one's 0.05, so halfway up to 0.1. There you go, spike graph. So far, so good? Nothing too scary, is it? Okay. Part D asks you to find the median and the mode, correct? Mode and median, yes. Mode and median. Well, mode is easy. Mode is just the most common one. Just what's the most common object? 2. So mode is 2. You know, most commonly purchased thing is 2 magazines. Mode, fancy X equals 2 magazines. Ah. But median's a little bit trickier. Yes? I'm sorry? We don't have part D on our paper. You don't have part D on your paper? No. I'm sorry. Yeah. Part D, find median and mode. Mode and median. That's weird. Find the mode and median. I'm sorry, go ahead and add that. I'm not quite sure how that happened. Find the mode and median. I must have edited it after I printed it. I'm sorry. Okay, cool. So you guys can see the mode relatively easy. Let's talk about the median though. What do we know about the median of a set? It's the middle, so it represents half, right? 0.5? Okay. Well, the probability that little x equals 1 plus the probability that little x equals 2 is 0.23 plus 0.38. And that number is 0.61. That's more than 0.5, right? But we know that x equals 1 only represents 23% of the data. That means that the 50th percentile, the Q2, must have landed in the 2s. So the median has to be little x equals 2. Because the 50th percentile fell somewhere between 1 and 2. So it's one of the twos.
Okay, what is the probability
Probability
x equals 1?
x equals 1 is 23%.
Yeah, and then why did you just add those two?
Well, because we know that the median is the 50th percentile, 0.5. And we know that 0.5 is bigger than 0.23. And when we add these, we surpass 0.5. So the 0.5 must have landed as one of the twos because it's after 20.23, but it's much less than where the twos end.
Okay.
Does that make sense?
Yeah.
Imagine you were listing them all out. You have 23 ones, and then you have 38 twos. The 50th term would have been one of the twos, is what we're talking.
Okay.
Is that better?
Yeah.
So imagine it's 100 terms. The 50th term, which is much more than the 23rd term, would have been one of the 38 twos. So that's what we know.
Okay.
And in fact, it would have been the average of two twos, I think, because it's an even number. Yeah, but it's still 2. All right. Let's flip her over. See what we got on the back. We have, come on now, catch up with me, panel. There we go. It says, show that the following is a probability distribution function. Let me ask you a question. How would we show that this is a probability distribution function or a probability mass function? How would we have done that? What must be true in order for it to be a probability distribution table, Julia? The probabilities have to add up to 1. There you go. That's it. The probabilities have to add up to 1, and you've been told that your domain is 1, 2, and 3, and 4. So the way that we show that this is a probability distribution function is we find what all the probabilities are and add them up. If they add up to 1, yay, we've done our job. If they don't add up to 1, we go, oh, that's not a probability distribution function or mass function. So let's see, what is the probability that capital X equals 1? Well, you literally plug x equals 1 into the probability distribution function. What you get is 1 squared plus 1 over 34. That's 2 over 34. Do not reduce your fractions. You want them all to have the common denominator of 34 so you can add them easily. Probability that capital X is 2. You plug in 2. 2 squared, which is 4, plus 1 over 34. So 5 over 34. Plug in x equals 3. 3 squared, which is 9, plus 1 over 34. 10 over 34. And lastly, plug in 4. I'm sorry? Wish it wasn't talking to me. 4 squared plus 1, 16 plus 1, 17. So 17 out of 34. And now we just add them. Well, I'm out of vertical space, so I'll have to write it over on the right side. All obey this property. That's important. You know, we can't have any negative probabilities. That's impossible. And we need all the probabilities to be between 0 and 1. We have that. And also, if we add up all of the probabilities, we get 2 over 34 plus 5 over 34 plus 10 over 34. That's 17 so far. Oh, and there's the other 17. I was going to write 17 again for some reason. Come on, active panel, you can do it. There we go. Squeeze it in there, probability. It equals 1. Therefore, yes, you have a probability distribution function. That's how you would do that if it was a test question. You would plug in all the x's, add them up, and see what they add up to. If they add up to 1, bingo, probability distribution function, as long as all the probabilities were positive and between 0 and 1. And if they don't add up to 1, well, then it's not a probability distribution function. Pretty easy, right? Yeah. Yes. You would have to show that they add up to 1 in order to prove that it is a probability distribution function. For your last example, there's only 2 parts?
Yeah.
Okay. Is there only 2 parts down here? Yes. Somebody say no when I move the board? Somebody still writing? Could have sworn I heard somebody say no. What's that? Yeah, okay, well, whatever. 2 marbles are randomly selected without replacement, okay, that matters, from a bag containing 4 red and 2 blue marbles. A capital X denote the number of red marbles selected. Talking about finding a probability distribution of X, and then illustrate the probability distribution using a spike graph. We did a spike graph last time. Just want to do a bar graph this time? It doesn't really matter much. Okay, let's change it to bar graph. It doesn't really matter. Whatever. Man, you know what would make this a lot easier to do? I mean, I don't know the probabilities, but you know what would help? Diagram of some sort. I'm feeling tree diagram. Yeah. Yes, tree diagram. Tree diagram. And what are our options? Red or blue? Our options are red and blue. So we pulling that first marble out. It's either red or it's blue. So event 1, like this. Well, what was the probability that it was red? 4 out of 6. That means the other probability must be 2 out of 6. Something just disconnected from my computer, but I don't know what. Figured it out. My calculator. Alrighty, so after that has been removed, there are still 2 possibilities. You could still have pulled a red or a blue, regardless of which one you chose. Of course, the probabilities will be different, though. Let's say that first marble was red. You pull it out, go, ooh, red marble, and you put it in your pocket. How many marbles are left? 5, but how many of them are red? 3. So we have a 3 out of 5 here, which means the other one must be 2 out of 5 because they have to add up to 1. The other option is you pulled out a blue marble and, ooh, it's blue, and you put it in your pocket. There's still going to be 5 marbles left, but how many of them are blue? Now there's only 1. So this is a 1/5, and the other one must then still be 4/5. So we have 4 different possibilities, but 2 of them are 1 red, because we were told to say that X is the number of red marbles. So X is equal to 0, 1, or 2. These are your only 2 options because you're only pulling 2 marbles. Let's see. If you multiply across the top, red is going to give you 4/6 times 3/5. I'm not going to reduce. Gives me 12 over 30. That is the probability that X equals 2. If you go red then blue, 4/6 times 2/5, it gives me 8 out of 30. But that is not the only way of pulling 1 red marble, because I could have gone down the blue-red branches, which would be 2/6 times 4/5, which, as it turns out, is still 8 out of 30. You see, these 2 are an OR statement, and they constitute the probability that X equals 1, because the red marble could have been first, or it could have been second. And whenever you're saying OR, you're talking about the addition law of probability. So it's going to give you 16 out of 30. And then last is X equals 0, or no red marbles. That's going to be 2/6 times 1/5. 2 out of 30. This is the probability that x equals 0. I forgot to write my probability up here. There you go. And yeah, 12 plus 16 plus 2 does add up to 30. Huh, that says 2/3. 2/30ths. There we go. Now that we have that, we can actually do part A. I say we just make a probability distribution table for x. Okay? 12, 16, and 2. A. We have x, and the probability that you get that number. 0, 1, 2. Now I know this isn't the order we found them in, but isn't it nice when your numbers count up from small to big? I think that makes life easier. Smallest probability was no red marbles, so 2 out of 30. The most likely scenario was you pulled one red marble, either first or second, came out to be 16 out of 30. And then the last one was when probability x equals 2, and we got, what, 12 out of 30? Yeah. Probability distribution table. And then part B just says to illustrate it with a graph. Do a bar graph this time, since we did a spike graph last time. X equals 0, x equals 1, x equals 2. And all these things are 30ths, and it looks like I went by 4s. I only have 4 tick marks on mine. 1, 2, 3, 4. So this was 4 30ths, 8 30ths, 12 30ths, and then 16 30ths. And then I just did my best. 2 30ths, so that's half of 4 30ths. So just try to go halfway. Boop. 1 reached all the way up to 16. And 2 went to 12. And that's all she wrote, folks.